All right, to start this review, I thought we'd review the parts of a neuron first. And the way I'm going to draw that is this is going to be the cell body. Okay, so this is the cell body. These are the dendrites. Pardon my drawing. All right, so cell body, dendrites. Here's an axon. And here's a synaptic knob. Remember, axons can branch and maybe have several different points of contact. All right, so they are labeled, and just as a reminder, the synaptic knob just doesn't end anywhere. It most likely ends on the dendrites of another neuron. Okay, so we'll just add a new neuron right there. In skeletal muscle, of course, that target was skeletal muscle. Then there are other targets. But for this chapter, we're most likely focusing on the synapse with a second neuron. So then we would have a presynaptic neuron, right, the one before the synapse, and a postsynaptic neuron, the one after the synapse. So just as, again, reminder, the dendrites is where signals are typically received. The neurosoma is where the nucleus is located. That's the main portion. I'm going to draw in here the trigger zone. I'm going to do that in blue. So here's the trigger zone right here, kind of ugly. So there's the trigger zone right there. I'm not going to label that. That's where our signals will start. That's the part that has to get to threshold in order to fire. And when we say fire, that means generate an action potential. The axon, of course, is the long, thin fiber. The action potential will go down that axon to the synaptic knob, which, of course, synapses with the target. This trigger zone right here is what we are primarily interested in to start and to generate an action potential. Remember that trigger zone consists of the axon hillock and the initial segment. Okay, it's the part before there is a myelin sheath, if there is a myelin sheath. And what I'm first going to talk about are EPSPs and IPSPs. Remember that both of these, both EPSPs and IPSPs, are local potentials. I'm sorry if that's not very readable there, but those are both local potentials. Okay? And EPSPs are excitatory local potentials. So if I am at a resting membrane potential of minus 70 millivolts. Threshold is at minus 55 millivolts. An excitatory local potential is when some type of a signal, typically it's going to be a chemical signal, so it's a ligand-gated channel. It's a ligand-gated sodium channel, and when a sodium channel is open, you should already know that sodium is going to move into the cell. And if it moves into the cell, the positive charge goes with it. Therefore, the interior of the cell becomes less negative. Okay? So, what we have then is that the local potential right here is due to sodium influx. And if that local potential, that local excitatory potential does not make it to threshold, then it will reverse. Because remember, local potentials are reversible. And so it'll come back down to minus 70, nothing will happen. Another property of these local potentials were they're local. They're not spreading anywhere. They're just staying right there. Okay? They got weaker with distance, so wherever this is happening on the membrane, it gets weaker the further and further away that you get. So that's an excitatory postsynaptic potential. An IPSP, or an inhibitory postsynaptic potential. Okay. Again, if we have our minus 55 threshold, and then we're at a resting membrane potential of minus 70, now there's the opening of a ligand-gated, it's either a potassium channel or a chloride channel. Okay? And so if a potassium channel opens and potassium is higher inside the cell, then that potassium will leave the cell, taking its positive charge with it, making the interior of the cell more negative. Okay, so we're moving away from threshold. All right, that's further from threshold. That's why it's inhibitory. It will make it more difficult to get to threshold. Now, we also mentioned a chloride channel. A chloride channel will have the same effect. If a ligand opens a chloride channel, chloride, which is in higher abundance outside the cell and is negatively charged, will bring its negative charge into the cell, therefore making it more negative. Okay? And so it's the same result. So a IPSP, again, is due to either potassium efflux or to chloride influx. And again, this is a local potential, so it is reversible and will eventually come back to resting membrane potential, assuming all other things are the same. Now, remember, these signals that are being received from either excitatory or inhibitory neurotransmitters are typically received out at the dendrites. Okay? And what is happening is there are many of these signals that are all being received at the same time. And the EPSPs are trying to make membrane potential less negative. The IPSPs are trying to make membrane potential more negative. And what we're doing is we're adding those all up together here at the trigger zone. Okay? So what we're primarily concerned with is what is happening at the trigger zone. Do we get to the threshold potential right here at the trigger zone, or don't we? Okay. So let's go to a new screen here and take a look. Now we're only looking at the trigger zone. Remember that, only at the trigger zone right now. And we're starting at a resting membrane potential of minus 70. Our threshold will be minus 55. We're going to add another value in here, plus 35. So now we're going to look at generation of an action potential. Okay. So we're going to start at minus 70, which is resting membrane potential. And then an excitatory signal comes along, causing the membrane potential to increase. And I'm going to draw this in a different color here to show this. So this is a local potential. In fact, it's a local potential that is probably derived of many EPSPs. There might be some IPSPs at the same time, but the EPSPs are overruling them. Remember, it's all how they add together. So this part right here is a local potential. It's an EPSP. All right, so the sodium that is coming in at that point is coming through ligand-gated sodium channels. Remember, the ligands that most likely open these channels were neurotransmitters released from another neuron, although there are some other reasons as well. Okay? And the sodium comes in, and if it never makes it to threshold, nothing will happen. But if you get to the threshold potential right here of minus 55, then we're going to have some things happen. The first thing that's going to happen is that this is the threshold potential. This is the voltage at which voltage-gated sodium channels open. All right, and because voltage-gated sodium channels open, remember we're talking at the trigger zone, and the trigger zone has a high density of voltage-gated sodium channels. Therefore, when it reaches the threshold potential, there is a very rapid influx of sodium into the cell. And so we see this very sharp change in membrane potential where the membrane potential actually surpasses 0, right, which would be about right here, and goes all the way to plus 35, right? This is the depolarization phase of an action potential. Right, so the sodium comes in, and remember, I'm not going to write it in here, but we just talked about where this comes from. The sodium, this rapid sodium influx right here, comes through these voltage-gated sodium channels that opened at the threshold potential. Okay, we said that two things happened when we hit threshold potential of minus 55. Okay, so here's the threshold potential of minus 55, and two things happened. One thing we already talked about, that's number one right here, and that's that the voltage-gated sodium channels are open. The second thing that happens is that this is also when the potassium gates, or the potassium channels, begin to open. But remember, those potassium channels are slow. They are slow potassium channels, and therefore they are not open during the depolarization phase of the action potential. But now we get to plus 35 millivolts right up here at the peak. And again, we are going to have two different things that happen, both of which are important. Okay? The first of those items that happens is that those voltage-gated sodium channels close, and remember, I said that they close tightly. All right, so that's the first thing that happens. The voltage-gated sodium channels close tightly. Because they close tightly, there's no more sodium influx, and so this peaks at plus 35. The second thing that happens is that the voltage-gated potassium channels are finally open. Remember, they started open down here at the threshold potential of minus 55, but they were slow. Finally, up here at about plus 35 millivolts, those slow potassium gates are finally open. So those are the two things that happen at plus 35 millivolts. Now think about it. The sodium channels are closed, so sodium isn't moving anymore, but potassium channels are open. And therefore, potassium is going to move. But which direction does potassium move? And you should know this, because potassium is higher inside the cell, and so now that the potassium channels are open, there's going to be an efflux of potassium to the outside of the cell. Well, that's going to cause a rapid change in membrane potential where it's moving, it was plus 35, but positive is leaving the cell. So it goes down, 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 it goes down. In fact, it goes all the way down to minus 70, and we'll continue it from there. So this is the repolarization phase of the action potential. And that is due to potassium efflux through the voltage-gated potassium channels. Now remember, during this same phase, that says depolarization. Let me fix that here. That's a typo. All right, so that is now correct. The repolarization is due to potassium efflux. Well, remember what the sodium channels are doing during this time. The sodium channels, I said, are closed tightly. All right, they're closed tightly. They will not open no matter what. That's important to understand some other things later on. But now we are down here at minus 70 millivolts again, which would normally be the resting membrane potential. So here we are. And there's two things that once again are going to happen. Okay, we had two things that happened at minus 55. We had two things that happened at plus 35. And now we're going to have two things that happen at minus 70. Okay, so let's draw them. I'll put them over here for the sake of space. We'll have number 1 and we'll have number 2. The first thing that happens is the voltage-gated sodium, voltage. Yes, I'm sorry, I was reading that. the voltage-gated sodium channels are reset. The ones that were closed tightly are reset so that they can now be opened again. The second thing that happens is the voltage-gated potassium channels, and that's where the potassium has been leaving the cell. The voltage-gated potassium channels begin to close. Right? But these voltage-gated potassium channels, remember, they were slow to open. Well, now they are also going to be slow to close. And because they are slow to close, potassium continues to leak out for a little bit. So the membrane potential goes down below -70. But then the channels are eventually closed all the way. And of course, the sodium-potassium pump is working all the time. So then potassium levels and everything returns back to normal right here. Okay. This particular portion right here is known as the hyperpolarization phase of an action potential. And that hyperpolarization is due to potassium efflux through those voltage-gated potassium channels that were still closing because they were slow to close. And then eventually it makes it back up to resting membrane potential at -70 again. Okay? And then everything is reset. So here it is again at -70. Well, this figure becomes really busy with all these labels, but what I strongly encourage all students to do is draw this out and label it yourself and be able to do it without having to read off of something else. There will probably be 6 to 7 to 8 questions on the exam, a large portion of the exam, where you can answer the questions if you merely know the information in this particular figure. All right, let's draw one of these action potentials now. Okay, so there's our action potential. What we're going to do here is label some of these different parts in a different way. We talked about the local potential, and I'm not going to label this here. So there's the part right there. We talked about the depolarization, which is the next phase, right? So this is the local potential. This is the depolarization. This right here is the repolarization. And then this part right here is the hyperpolarization. And of course, this section here and this section here are the resting membrane potential. But now let's talk about this in terms of refractoriness. Remember, a refractory period in terms of an action potential is the time during which you cannot generate another action potential. So let's draw our neuron once again. And this part right here, this is our trigger zone, okay? So this is the trigger zone right here. I'm just going to abbreviate TZ, trigger zone. This action potential that we're talking about is only measured at one place on the membrane. So obviously, it's only occurring at one place, but yes, we talk about it traveling, and we'll talk about that in a moment. But what keeps it traveling in only one direction is this idea of a refractory period, okay? Because the action potential cannot be regenerated during a refractory period. Okay? So there's two parts of the refractory period. The first part of the refractory period starts right here. That's the beginning of the action potential when the trigger zone first, or it could be in another part of the membrane as well, but when it first hits threshold. And that refractory period remains until we get over to here, down to -70 again. So this is the absolute refractory period, and I'm going to indicate that here by these two blue lines. Now there's two reasons that this is an absolute refractory period, meaning no matter what else happens, this part of the membrane cannot generate another action potential. The first happens during the depolarization phase of the action potential, during this portion right here. Okay? Well, during this portion of the action potential, all of the voltage-gated sodium channels are open. Well, they're already open, therefore you can't generate another action potential, because to generate an action potential, you have to open the voltage-gated sodium channels. They're already open. So it's refractory for that reason. The other reason you can't generate an action potential during this time is, remember, right up here at plus 35 millivolts, we said that the voltage-gated sodium channels are closed tightly, okay? And that they remain tightly closed until we get down here to minus 70. So during the repolarization phase of the action potential, from plus 35 to minus 70, the voltage-gated sodium channels are closed tightly and cannot be reopened. Therefore, no matter what else happens, the sodium channels cannot reopen, and therefore another action potential cannot be generated. Okay? And for that reason, this, between these two lines right here, is the absolute refractory period. Well, we also talk about a relative refractory period. And the relative refractory period is between these two green lines. Okay? Note that that coincides right here with the hyperpolarization phase of the action potential. Now, remember that at minus 70 millivolts right here, that the voltage-gated sodium channels reset. So they can be opened again. Therefore, another action potential can be generated. However, it's harder to generate that action potential because this hyperpolarization phase, the membrane potential is further from the threshold potential of minus 55. So it's harder to generate that action potential, but it could be done with an appropriate, with a strong stimulus, would be able to do that. And therefore, we refer to this phase right here between the two green lines as the relative refractory period. All right, so those are the refractory periods. Now let's talk about the propagation of an action potential down an axon. All right, so I am going to draw, let's start here with the trigger zone and go down an axon to a synaptic knob. Okay, and right here between these two lines, this is the trigger zone. Okay, once again, the trigger zone has a high density of voltage-gated sodium channels. Now, in terms of propagating the signal down the axon, of course, when the trigger zone hits the threshold potential and fires, there's a large amount of sodium that comes into the trigger zone. And it diffuses in all directions, including this direction, right? Well, all the way down the axolemma, these little black marks, and they're on both sides, they're not on just one side, but I'm only going to draw them on one because it makes it too confusing. All right, these are voltage-gated sodium channels. And as the sodium diffuses down the axon, it opens the next set of voltage-gated sodium channels. Well, if we open voltage-gated sodium channels, and I'm going to switch to show sodium here in red. All right, so the sodium comes in. Again, it diffuses in all directions, but it diffuses a little bit this way. And that opens the next set of voltage-gated sodium channels. More sodium comes in. It diffuses both directions, opens the next set of voltage-gated sodium channels, and you get the idea. We're going to open them all the way down the axon until we get to the end and we release neurotransmitter. Okay? This is how propagation of an action potential occurs in an unmyelinated axon. This is the same way that it occurred in the sarcolemma of skeletal muscle, that the influx of sodium opened the next set of voltage-gated sodium channels, so it kept opening the subsequent channel. Now, remember, the sodium is diffusing in both directions. So why doesn't it reopen the channels in this direction and have the action potential move back up the axon away from the synaptic knob and toward the cell body? Well, that's because this area of the membrane that just had an active potential, that's where this sodium came from, is in the refractory period. It's in the absolute refractory period. And therefore, even though sodium diffuses in, the signal can only go one direction. Okay? So the absolute refractory period ensures that the direction of the signal only travels from the cell body toward the synaptic knob. But it also sets an upper limit on how frequently an axon can fire, right? Because if it's going to have one active potential and then it's traveling down the membrane, if there's an absolute refractory period, it's going to be a little bit before the next active potential can fire. So you might have an active potential here, you might have one here, you might have one here, you might have one here, and all the way down the membrane. But they can only get so close together because there is a limit in how frequently that can fire. Okay? Now that is in an unmyelinated axon. In a myelinated axon, so again, here's the trigger zone. And we go down, and here's our synaptic knob. But this time, we are going to surround parts of the axon with a myelin sheath. And I'm going to make that myelin sheath kind of a gray color. In reality, myelin is white. And so this part of the axon is surrounded by a myelin sheath. Okay? And then there's a break. And there's another myelin sheath. Remember, in the peripheral nervous system, these are formed by Schwann cells. In the central nervous system, these are formed by oligodendrocytes. Let me draw a couple of more here. So each one of these little gray segments represents the myelin sheath. Now, just by the way of review, and I'm not going to write these words down on the animation here, but I want you to remember that the parts of the axon that are covered by a myelin sheath, that's the part bracketed here in blue, in fact, maybe I will label this, that is the internode. Okay? And the part that is between the internodes, this section right here, that is a node of Ranvier. And we'll talk about the nodes of Ranvier in a moment because they're important for the way that a signal is propagated along a myelinated axon. Remember that it's faster on a myelinated axon. So let's go back and remind you that this here is the trigger zone. Okay? And that trigger zone is special. Okay? Remember, the trigger zone, TZ for trigger zone, has a high density of voltage-gated sodium channels. So that when it gets to threshold, there's a large influx of sodium. Well, in an unmyelinated axon, we saw that that sodium could open the next voltage-gated sodium channel, which would open the next voltage-gated sodium channel, and all the way down the axon. But in a myelinated axon, and once again, we'll also show sodium here is going to be in red. When the sodium comes in, it diffuses down and it's getting weaker, it's getting weaker, it's getting weaker, but there's just enough sodium that hits the part of the membrane at the node of Ranvier. The node of Ranvier also has an extremely high density of voltage-gated sodium channels. And I'm not going to type that in because that's a lot of words. So the voltage-gated sodium channels that are a very high density at the node of Ranvier. And I'm about out of time for this particular slide, so let's hurry here. But this sodium, if these are voltage-gated sodium channels, it opens those. And now there's sodium influx. And it diffuses down and opens the next set of voltage-gated sodium channels at the next node of Ranvier, which opens the channels at the next node until it gets to the end. This is known as saltatory conduction. And this is how signals are faster in a myelinated axon, because they jump essentially from node of Ranvier to node of Ranvier, where there's a very high density of voltage gated sodium channels.